Our next presenter is Anna Naranjo, a PhD student from UC Davis, who is working on research related to the life cycle assessment models to evaluate whole farm greenhouse gas emissions.
Hello, I am Anna Naranjo, a PhD student at UC Davis in the Animal Biology Graduate Group. My work is focused on the environmental impacts of livestock production, and today I will be sharing my work on the environmental impacts of the California dairy industry over 50 years. Since two of our models are based in 2014, I will share a few points. In 2014, California was the leading milk producing state, with 1.8 million cows producing up to 24,000 pounds of milk per cow per year. This brings total milk production in California to 42.3 billion pounds of milk per year, which is great news for milk lovers. However, there is growing concern over greenhouse gas emissions in all sectors. Agriculture alone is responsible for 10% of total greenhouse gas emissions and 38.9% of total methane emissions. To meet California's greenhouse gas goals of reducing methane emissions from the livestock sector by 2030, we need to know where we stand and where to make improvements. To reduce emissions, we need to first determine what is our baseline. We do this using life cycle assessments or LCAs. LCAs let us look at a product from start to finish. It allows us to compare across similar products, and LCAs are becoming the standard when comparing environmental impacts of products. The goal of this project is to conduct a Cradle to Farm Gate LCA of 1964 and 2014 with respects to greenhouse gases, water use, and land use, and we want it to be California specific. Additionally, the 2014 model will be the base model for scenario analysis. We followed international guidelines to create uniform, comparable models. The ISO guidelines are used as a framework for all LCAs. The LEAF guidelines are used specifically for livestock supply chains, and the IPCC guidelines are used for greenhouse gas quantification. We use the IPCC's Assessment Report 5 for greenhouse gas reporting, which equates methane to be 28 times more potent than carbon dioxide and nitrous oxide as 265 times more potent than carbon dioxide. Our system boundary defines what we include and exclude in the model. Here we include feed production, animal husbandry, and manure management, including everything upstream. We sum all the emissions and calculate based on 1 kilogram of energy corrected milk, or ECM. Within feed production, we include seed production, fertilizer production and application, fuel production and combustion, energy to pump water, transport, pesticide production, and so on. Animal husbandry includes the energy and water required to run the farm and milking parlors. We also include enteric methane from the animals. Manure management emissions depend on the amount of manure generated, how it is stored, and its final use. Because we are looking at a livestock product, we also take into account the life cycle of the animals. We track all the inputs and products from the calf stage through for lactation. We are comparing 1964 to two models for 2014. Data for 1964 rations are from literature reviews, and milk values are from the United States Department of Agriculture. Data for 2014 Model 1 is primary data from 5 commercial dairies, and data for Model 2 is from cost of milk production reports from the California Department of Food and Agriculture. From the rations, we obtain the nutrient composition using the dairy NRC. The nutrient composition will be used to calculate enteric methane and manure management emissions. This is an example of the cost of production reports used to build our California-specific feed inventory. They provide information on regions and yields, quantity of irrigated water, fertilizer use, pesticide use, and energy used on the field. These values and emission factors were used to create our California-specific feed inventory. To calculate enteric methane, we used the 2013 Nielsen model. For manure management, we followed the IPCC guidelines for calculating emissions from manure, except we selected different models for volatile solids and total manure nitrogen, as these models have a better fit. For 2014, the proportions of manure in each management system was from the California Air Resources Board. Due to lack of data for 1964, we spoke to an expert. Notable items include the increased use of anaerobic lagoons in 2014 and only using pasture and liquid slurry for 1964. This is essentially what our model is. We have crop production, animal husbandry, plus enteric methane, and manure management, all divided by the total milk production. However, because at the end of life of the animal, we have meat as a co-product, we need to take that into account. And we do this by using a biophysical allocation factor based on the total milk and meat produced. We then apply this factor to all categories that can be attributed to both beef and milk production. In 2014, the allocation factor determines that milk receives 92% of the burden, while 1964 milk only receives 81% of the burden. Additionally, because data for on-farm energy and water use was not separated by activity, we could not allocate emissions. Therefore, milk carries the full burden. All of this combined, allocated, and divided by the total milk production gives us the emissions or resource use per kilogram of energy-corrected milk. We can see that total greenhouse gas emissions were reduced by 41 to 45% from 1964 to 2014. Most of the reductions are due to the more than double milk production in the last 50 years. Crop production decreased 62.6 to 63.9%. Much of the reductions are from improved crop production yields reached by using efficient fertilizer application, plant genetics, and biotechnology. Additionally, improved ration efficiency and increased byproduct use also contributed to the reduced emissions. Enteric methane was decreased by 54.1 to 55.7%, again due to milk efficiency improvements and improved feed efficiency. Manure management decreased by only 8.7 to 11.9% due to a switch to mostly anaerobic lagoons in 2014, which has the highest methane conversion factor. As we mentioned earlier, in 1964, it was assumed all heifers were on pasture and cows on liquid slurry. Reductions in total water use were 88.1 to 89.9%. Majority of the reductions were due to improvements from crop production. Due to the lack of data for 1964, housing and milking water use reduction was due to the improvements of daily milk per cow entirely. Total land use by crops was reduced by 89.4 to 89.7%. Once again, reductions were due to improvements in crop production and milk efficiency. Continued improvements in crop production will reduce land use, water use, and greenhouse gases. Per unit of milk production, greenhouse gases, water use, and land use decreased considerably in the last 50 years. Both 2014 models were on the lower end compared to higher income countries, and both our 2014 models were lower than the national average at 1.23 kilograms of CO2 equivalents per kilogram of energy-corrected milk. As the highest contributing categories, manure and enteric methane present opportunities to mitigate emissions. The next step for this project is to explore mitigation strategies for the whole system. These strategies might include alternate energy sources, feed additives, manure management technologies, and more. Large-scale national models, maybe even state-level models, may miss the variability between farms, so not all conclusions or mitigation strategies would apply to a given farm. The goal would be to have more models, but at a smaller scale. Producer-level models would be much more specific, and all mitigation strategies would apply. To motivate producers, there should be a premium for sustainably produced milk or a carbon credit for reducing greenhouse gas emissions. The published paper and references can be found using this QR code. I'd like to thank you for your time and feel free to email me questions.